The short video is going to recap some of the basic concepts of graphs of motion. And we're going to look at three different kinds of graphs. The first is a displacement time graph. Remember, displacement is a vector quantity, distance is the scalar quantity, and displacement relates to your change in position over time. It's given the abbreviation delta x if the displacement's in the horizontal direction, or delta y if it's in the vertical direction. And of course, displacement is measured in meters. Second graph we'll look at is a velocity time graph. Velocity is your rate of change of displacement. Its symbol is v, measured in meters per second. And it's the vector quantity similar to speed, which is the scalar quantity. And then the third graph we'll look at is an acceleration time graph. And acceleration is your rate of change of velocity, symbol A, measured in meters per second squared. So let's start off by having a look at a displacement time graph. This might be a typical displacement time graph you might come across. Notice that the y-axis is displacement, measured in meters, and the x-axis is your time axis. And let's start by considering the gradient. The gradient of a displacement time graph is your change in displacement, delta x, over your change in time, delta t. And of course you remember that delta x over delta t is simply your velocity. So the gradient of a displacement time graph gives you your velocity. So if we have a look at this little portion of the graph drawn there in blue, you'll notice that it has a constant gradient. It's a positive gradient, and so here we have a constant positive gradient, and we've just seen that the gradient is the same as the velocity. And so that portion of the graph shows an object moving with constant velocity. The next little portion of the graph, between 2 and 3 seconds, the gradient's essentially flat there, so the gradient's 0. So between 2 and 3 seconds, this object remains remains constant or stationary at just over 20 meters in terms of displacement. And so that part of the graph shows a delta x that's constant, a constant displacement, and that shows us that the velocity is 0 at that point. This portion of the graph over here, between about 3.5 and 5 seconds, again a straight line indicating constant velocity, but in this case we have a negative gradient. And so that part of the graph shows a constant negative velocity. In other words, the object now is returning in the opposite direction, and you can see after 5 seconds it's returned back to where it started at 0 displacement. Let's have a look at this particular example of a displacement time graph, and we're going to look at each section individually. If we start with this portion between A and B, you can see we've got a curved shape to the graph with an increasing gradient. And remember, a gradient tells us velocity. And so during that portion of the graph, the velocity is increasing, and hence that shows acceleration. Between B and C, we have a straight line displacement time graph. The gradient's constant, and so that shows an area of constant velocity, and because there's a positive gradient, it's a constant positive velocity. Between C and D, the displacement is constant, and of course what that means is that the object's not moving. And so whatever object this is stationary, and the velocity between C and D is 0 because the gradient is 0. Between D and E, we now have a negative gradient. Once again, it's a straight line, so it indicates constant velocity, but it's constant negative velocity. And of course that negative sign indicates direction. And so this shows us that between D and E the object's going in reverse. It's going in the opposite direction to motion. So those are our displacement time graphs. Key thing to remember there is that the gradient shows you velocity, and we can have a curved graph which will indicate acceleration, a straight line which indicates constant velocity, and a horizontal line which indicates 0 velocity. Let's go on to our velocity time graphs. Second type of graph we'll come across. Here's a very typical velocity time graph. Your y-axis, you'll notice, is a velocity axis in meters per second, and your x-axis is a time axis. Now, two important things to consider here. Firstly, the gradient. What does the gradient of a velocity time graph tell us? Well, the gradient is the change in the y-axis over the change in the x-axis. And so if we apply that to this, the y is velocity, so it's change in velocity. The x-axis is time, so it's change in time. And of course, delta v over delta t gives us acceleration. So the gradient of a velocity time graph tells us acceleration. If we then consider this shaded area in green, what we call the area under the graph, what does that tell us? Well, the area under a graph would be calculated by taking the one axis and multiplying it by the other, taking into account for the shape. But in this case, we've got change in velocity multiplied by change in time. And I hope you remember from your simple motion formulas that that just gives us displacement. So two key things to remember for velocity time graphs. The gradient gives you acceleration, and the area under the graph gives you displacement. So let's have a look at this particular example. Notice that the velocity axis is measured in meters per minute. It's not SI units, but still a valid measure of velocity. And the x-axis, the time axis in minutes. This first area between for the first 10 minutes of the motion, we see a straight line graph, and a straight line velocity indicates that the velocity obviously is increasing, but the gradient, remember, tells us acceleration, and that gradient's constant, and it's positive. So the velocity there is increasing, and the acceleration is constant. Between 10 and 15 minutes, this little portion of the graph there indicates a constant velocity. So this particular object is traveling at 60 meters per minute, and during that time the velocity remains constant, and so there's no acceleration. So the gradient of that portion is 0, and hence the acceleration is 0. This portion over here, between 15 and 30 minutes, shows a negative gradient and therefore a negative acceleration. And what that means is that the object's slowing down from 60 down to 0. And so here we show a velocity that's decreasing. In other words, we have a negative acceleration, an acceleration less than 0. And then at this point over here at 30 minutes, the object has come back to a velocity of 0. In other words, it's stopped. The graph, however, continues in the opposite direction, that little green portion. And for the next 10 minutes, we have an increasing velocity, but it's in the negative direction. Remember, the positive and negative simply indicate direction. So here we have the object now just traveling in the opposite direction. It's accelerating in that direction, and because that direction is the negative direction, we have a negative gradient of that part of the graph. This last portion, between 40 and 55 minutes, once again shows a positive gradient. So we have a positive acceleration greater to 0, and in the context of this graph, it means that the object is slowing down from minus 40 back down to 0 and coming to a stop at 55 minutes. And then our final kind of graph is the acceleration time graph, and it might look something like this. This is not a difficult one to do, because our syllabus that we're going to be studying only deals with constant acceleration. And so the only graphs we'll ever come across related to acceleration time are horizontal straight lines. So all our acceleration time graphs will be horizontal graphs, either with a positive acceleration or a negative acceleration, or potentially a 0 acceleration. One of the more common motions we'll study is objects falling under gravity. And if an object does accelerate under gravity, it's a constant at minus 9.8 meters per second squared. The minus is indicating it's accelerating in a downwards direction. So this graph that we have on the screen at the moment might well be a graph of an object falling under gravity, with that red line indicating constant acceleration, possibly of minus 9.8 if it was under gravity.